Okay, so for this problem, what we have is a cantilever beam with 2-point loads. And what we're going to do here is we're going to look to solve for the shear and the moment diagrams for this beam due to the applied load. So first, what I went ahead and did is I already went and solved for the reactions here. And if you're not sure how to do that, I'll just write it down quickly, because for this type of beam, it's pretty straightforward. But if I write down for my reactions, all I have to do is, sum forces in the x direction equals 0, well, ax equals 0. It's the only x force, right? That should be pretty straightforward, right? Sum of the forces in the y direction equals 0, right? Any forces going up are going to be 0. Well, we have ay, minus 2 kips minus 3 kips equals 0, so ay equals 5 kips. Okay, so again, pretty straightforward. And sum of the moments is similar, right? Anything that's causing a counterclockwise rotation, we're going to say is positive. So what do we get? Well, we get the moment at A, and then we can get here minus 2 kips times our distance of 6 feet, minus 3 kips times our distance of the whole distance of 10 feet. There are reactions, and we get, this has to equal 0, so we get the moment at A equals 42 kip feet. Okay, so that's good. We got our reactions, we solved for those, and we can check box 1. Well, what we want to do next is we want to draw our shear diagram. And just like with simply supported beams that have a pin and roller, we work from left to right, and where the force goes up, our shear goes up. So we're going to start at 0. So this is going to be 0 shear, and then we're going to hit, as soon as we go to the left here of this beam, and as we're going to the right, we're going to hit a y, and that's going to bring us up 5 kips. So let's draw that in, and we'll label that 5. And we already have kips over here, so we're good with the units. And here what we notice is the force doesn't change anywhere between the 5 kips all the way till we get to the 2 kips. So the shear diagram is not going to change either. So we can just continue the shear diagram straight to the right, until we hit this 2 kip point load. And once we hit that 2 kip point load, we're going to come down 2 kips. So we can draw that line in and come, over here where we're going to label this. If we drop from 5 down 2 kips, we're going to be at 3 kips. And again, similar to what we did here, between the 2 kips and the 3 kips, there's no applied force, so the shear doesn't change. So as we come, we are going to be able to continue that line over and then straight down to close to 0. So let's draw those. So once we close to 0, our shear diagram is complete. So I'm just going to highlight this in, and we're going to call it a complete shear diagram. And if you remember, what we want to do next is we want to go ahead and we want to basically come here, and we want to now find some areas. So I'm going to find break this into logical areas, anywhere there's a change. So I'm going to break this into what I'm going to call like area 1 and area 2. And when we go to solve for our moment diagram, right, we've already gone and drawn the shear diagram, but when we go to solve for the moment diagram, what we need to do is we need to find those areas. So let's start with area 1 equals, what do we have? We have a height of 5, 5 kips, and I don't have to label it, but sometimes it helps. It's nice. So 5 kips times, what do we have? The distance here is this distance, which is 6 feet. And what do we get? We get 30 kip feet. Okay, and likewise, we're going to say the area 2 is going to be just another rectangle. So 3 kips, right, times our distance of 4 feet. So 3 kips times 4 feet, and that's going to be 12 kip feet. Okay, so what that tells us is it tells us the change in moment kind of from point 0 to point 1 to point 2, right? So if this is 0 here, and then we have point 1 and point 2, these areas are going to tell us the change in moment. And what we have to do, what's different about a cantilever beam, is that at the end of this cantilever beam, we have an applied moment. So unlike the other cases, that maybe are a simply supported beam that don't have an applied moment at the end, here on a cantilever beam, right, if you picture this beam bending, right, and we can draw in like a deflected shape of this thing's going to want to bend where it starts to curve down due to those loads, right? So this beam is going to curve down due to those loads. And what that is going to do is it's going to put tension in the top and compression in the bottom. And that informs us what our moment is. In general, if we have a beam, and I'm just going to sketch in kind of any old beam here, right? And what I'm going to say is, like, let's say we have just like a simply supported beam, right? And we put a load on it. Well, what's going to happen to that? That's going to want to bend like this. And typically what that's going to do is it's going to put tension on the bottom and compression on the top. Well, when we have a cantilever, right, and we have a cantilever that looks something like this, right, what happens now is our bending reverses and we end up with tension on the top and compression on the bottom. So what we need is some sort of sign convention. And I don't know if this was done on purpose, but typically what we have is if we have a situation, where we have compression on the top, tension on the bottom, we're going to call that situation positive bending. Looks kind of happy. I don't know, maybe you can make a little smiley face out of it. But if we go the other way and our curvature is reversed, right, this becomes negative. Okay, and that's one way that I kind of remember it. Positive has compression on the top, tension on the bottom. Negative has tension on the top, compression on the bottom. So when we come back to our cantilever and we look at this thing, we say, well, tension's on the top, compression's on the bottom. And that means that internally, this moment is going to look like this one. It's going to have a curvature that goes down like this with tension on the top, compression on the bottom. We have to start negative. So here, what we know is when we look at the moment at 0, this has to equal the moment at A. And typically with simply supported beams, the moment at A is 0. There is no applied moment. But here we have a rigid, a rigid connection. Like if we call this point A, we have a rigid connection right at point A, and that's going to restrain rotation, which is going to cause moment. Anytime you see curvature in a beam, you can start to think there's got to be a moment there because there's tension on one side and compression on the other. So in this case, the moment at O is going to be, MA, which equals 42 kip feet. And this gets a little tricky because we drew our arrow in the correct direction. So a lot of times what we'll do is we'll say, well, this is 42 kip feet, and we won't call it negative. But when we look at our sign convention over here, right? So this is our sign convention for internal moment, right? This is, let me put this up here, internal moment. We know that we have to start negative, right? This is putting tension on the top, compression on the bottom, just like this, and we have to start negative. If you can't remember, just think, like typically with cantilever beams, typically we're going to start negative. So we're going to come down here and we're going to start at, minus 42. So I'm just going to come down here and I'm going to say this is minus 42. Another way to think about it, right, is the height of the shear diagram has to equal to the slope of the moment diagram. So what does that mean? Well, here we have a positive height on our shear diagram. So that means we have to have a positive slope. So if we start down, we're going to start going up and keep going up until we come back to 0, right? That's what we want. We want to end with a 0 moment here. However, if we started, with our moment diagram way up, at 42 up here, and then went up and went up, we'd end up with some huge moment at the end, which we know it doesn't happen because there is really no tension or compression at the end of this beam. All right, so hopefully that makes a little bit of sense. And let's draw that line in to start. Okay, so there's the first line. And then what we're going to do is we're just going to carry on, right? So we have the moment at 1 has to equal, well, M0 plus A1. And typically, again, with simply supported beams, it's M0. Doesn't exist. It's 0. So, you don't have to worry about it. But with cantilevers, you do, because there's going to be bending. There's going to be rotational restraint at the support. So when we put this together, what do we get? Well, we get minus 42 kip feet, plus 30 kip feet, and that gets us to minus 12 kip feet. Okay, so we know when we add up the moment at the support plus all this area, right, what we're going to get to is we're going to come to 12 kip feet, or minus 12 kip feet. So we'll call this minus 12, and what we need to do is connect this with a straight line, because a constant height shear diagram turns into a straight line sloping moment diagram. So let's draw that line in. And then let's look at M2. So M2, we're going to have, basically M1 plus A2. And what do we have here? Well, minus 12 kip feet, plus 12 kip feet closes us back to 0, right? So we know we end back at the 0 point, and that's a good thing, right? We know that's where we want to end at the end of this beam. This is a free end of a beam with no applied moment, no applied moment over here, just a vertical force, but there's no applied moment, so we should end back at 0. So let's draw that line in. And once we draw the line in, we can just come back and shade this in because we are good to go, right? This is our moment diagram, and we solved it. nailed it, and we're good. All right, so hopefully that helps. And if it does, feel free to drop a like. If not, feel free to drop a comment. Anyway, if you have questions, hopefully I'll hear from you. Otherwise, keep working hard and keep moving onward and upward.